Welcome back to NephroTube online nephrology lectures. In this lecture, I will continue discussing a new chapter of NephroTube synopsis of conventional hemodialysis. In the first lecture, we discussed chapter 1, which was about principles of hemodialysis. In this lecture, I will discuss chapter 2, which is about extracorporeal blood circuit of hemodialysis. In the description of this video in YouTube, below the video, you will find some important links. The first link is a link to this same lecture, but in Arabic language, for those who like to watch the lecture in Arabic. You will find also a link to the playlist of video lectures about this book. You will find the link for the English playlist and Arabic playlist. You will find link to download this book for free. You will find link to download the PDF of this lecture for free if you like to use it. You will find the link for my website NephroTube, nephrotube.com, where you will find more lectures about nephrology than hemodialysis lectures. And finally, you will find a link to NephroTube social media accounts, the WhatsApp group, the Telegram channel, the Facebook group. You can join us to be always updated by the activities of NephroTube. And finally, it's better to subscribe to our channel and to make the notifications on from our channel, so you will be notified once we upload new lectures. This is my talk outline. I will cover extracorporeal blood circuit components, priming volume, blood tubing set sterilization, and finally extracorporeal blood circuit related alarms. Starting by extracorporeal blood circuit components. The extracorporeal blood circuit is generally consists of three components: the blood pump, blood tubing set, and dialyzer. Let's start by discussing the blood tubing set. The blood tubing set is formed of two components. The first one is the arterial segment, which is also called the inflow segment. It is called the inflow segment as it brings blood from the patient into the dialyzer. Through the blood, through the arterial segment, you will find the blood pump, which is one of the components of the extracorporeal blood circuit that I will discuss within few slides. Within this arterial segment, you may find also a sampling port. You can find a site for solutions infusion. You can find the site of heparin pump. In the arterial line, there are two monitors for arterial pressure. One of them is pre-pump. It is called the pre-pump arterial pressure monitor. It is present between the vascular axis of the patient and the blood pump. So it is present here between the vascular axis and the blood pump. Another pressure monitor is called post-pump arterial pressure monitor. It is present between the blood pump and the dialyzer. This arterial segment itself is divided into three different segments. The first part is called the pre-pump segment, which is the part of the arterial line before the pump. It is between the vascular axis and the pump itself. It is formed of polyvinyl chloride. The second part of the arterial line is the part of the arterial line which is within the blood pump itself. This part is formed of silicone wrapper, which is a thicker and more rigid material, and this is important for the action of the blood pump itself, as I will discuss later that the blood pump compress and milk the arterial segment. I will talk about that later on. The third part of the arterial segment is the post-pump segment. It is also formed of polyvinyl chloride as the pre-pump segment. So the first part, as we mentioned, of the blood tubing set is the arterial line or the arterial segment, the inflow segment. The second part is the venous segment or outflow segment. This segment returns blood back to the patient from the dialyzer. When the blood moves out from the dialyzer, before it reaches the patient, it passes first through what is called the venous drip chamber, which has an air detector, and we will talk about the function of this air detector later in this lecture. After that, the blood is returned back to the patient. At the venous drip chamber, there is also a pressure monitor for the venous pressure. And finally, below the venous drip chamber, there is an air detector clamp that we will discuss also later at the end of this lecture. Finally, as we mentioned in the first lecture, that in the dialyzer, the blood flow is in parallel to dialysate flow. The dialysate enters the dialyzer from the dialysate circuit, and the dialysate circuit will be discussed in details starting from the coming lectures. So we discussed now the first component of the extracorporeal circuit, which is the blood tubing set, which consists of the arterial segment or arterial line and finally the venous line. The second component of the extracorporeal circuit is the blood pump. The blood pump is considered as a roller pump. It works by occluding the intra-pump segment of the blood tubing set. That's why it must be rigid. The intratubular segment must be rigid. As we mentioned, that the pump segment of the arterial segment is formed of silicone rubber. Then after the pump occludes the arterial segment, the pump then draw this obstructed segment forward. So the pump is rolling forward, compressing part of the arterial line, then move it forward. Then it moves it forward, causing what is called the milking motion. This milking motion will cause the propulsion of the blood forward by the negative pressure that is caused by this milking action. So this milking action, by that the pump compress the arterial line, then push it forward, causing a negative suction pressure that will move the blood forward. The amount of blood that is pumped per one pump of the blood pump is called the stroke volume. The stroke volume of the pump. Okay. As I mentioned, that the part of the arterial segment within the blood pump must be rigid to be able to maintain the blood flow. Because if this pump is, if this part of the arterial line within the blood pump is not rigid, it may be flattened and become weak, and the stroke volume of the blood pump will be low. Finally, the blood flow rate that can be done by the blood pump ranges from 200 to 500 ml per minute, and its median, as we know, is 350 ml per minute. So now finally we finished the first part of the extracorporeal circuit, which is the blood tubing set, and the second part is the blood pump. The third part of the extracorporeal circuit is the dialyzer, but we will talk about the dialyzers later on separately in chapter 5. After talking about the extracorporeal blood circuit components, our second point to discuss in this lecture is extracorporeal blood circuit priming volume. First of all, what is the definition of a priming volume? Priming volume is the volume of blood filling any compartment. So this volume of blood that can fill the arterial line, the venous line, the dialyzer is called the priming volume of the blood. The priming volume of blood that can fill the blood tubing, arterial plus venous blood tubing set, ranges from 100 to 150 ml, and the priming volume of blood that can fill the dialyzer ranges from 60 to 100 ml, depending on the type and the surface area of the dialyzer itself. So when we calculate all the priming volume of the all extracorporeal circuit, I mean the priming volume of both the blood tubing set and the dialyzer with each other, it will be ranging from 160 to 270 ml. And this amount of blood is out of the patient body, and it may precipitate hypovolemia in the patient. So you have to put this in mind. The second point to discuss is the blood tubing set sterilization. The commonly used sterilizing agent is ethylene oxide. Actually, ethylene oxide within the tubes must be rinsed very well before connecting the tubing set to the patients. So, a thorough rinse before connecting the tubes to the patient must be done to avoid the allergic reactions that may be precipitated by the ethylene oxide if it entered the patient blood. And you have to put in mind that ethylene oxide may hide during rinsing into the heparin line or in any connector, small connector or side branch of the tubing set. So it is important and essential to flush the heparin line and any other side branches during the rinse cycle to remove this hidden ethylene oxide. Because if we didn't do that, and there is ethylene oxide, for example, is hidden in the heparin line, so when the heparin line starts to work, it will push heparin and ethylene oxide into the blood tubing set, which will reach the patient blood and cause allergic reaction. So it is important and essential to flush the heparin line and any other side branches during the rinse cycle. The coming point for discussion related to the extracorporeal circuit is the alarms related to the extracorporeal circuit. We have two alarms related to the blood circuit, which are the pressure monitors and the air detector. Starting by the pressure monitors. First of all, what are the pressure monitors, where they are present, and what is the normal range of pressure in each of them. First one, as we mentioned in the first slide, is the pre-pump arterial pressure. It is present between the vascular axis of the patient and the blood pump, so it is present in the pre-pump segment of the arterial line. The pressure in this area is usually negative, is always negative, ranges from -60 to -200 mmHg. The negative pressure in this area caused by the milking action of the blood pump. As we mentioned, the blood pump is milking the blood, causing a negative pressure behind it. The second pressure monitor in the extracorporeal blood circuit is the post-arterial pressure monitor. Also, it is called in some references as inflow pressure monitor. It is present in the post-pump arterial segment between the blood pump and the dialyzer. The pressure in this area is always positive, and it reflects the resistance that the blood found within the dialyzer. The third pressure monitor is the venous pressure monitor. It is present in the venous drip chamber. The pressure in it is from +60 to +200 mmHg, so it is also positive. An important point that the positive pressure in the venous pressure monitor is always lower than the pressure monitored in the post-pump arterial blood pressure. arterial pressure monitor. What makes the pressure falls from the post-pump monitor to the venous pressure monitor? This decrease in pressure reflects the influence of ultrafiltration done by the dialyzer. So this ultrafiltration will decrease the pressure in the venous limb than that of the post-pump arterial pressure. So what are the abnormalities or changes that may happen in each of these pressure monitors? What may makes them higher or lower? Let's start by changes that may affect pre-pump arterial pressure monitor. What may make the pressure in this area less negative, and what may make the pressure in this area more negative? The following may cause less negative pre-pump arterial pressure. Any air that may found before the pressure monitor, any entry will cause less negative pressure, as separation between the patient's vascular access and arterial line, or air leaking in any of these in any part of this arterial segment, or any air leaking between the patient vascular access and the bloodline. So any air entry, whatever the way or the method, before the pre-pump arterial pressure monitor will cause less negative, because it will decrease the negativity, which means increase in the pressure in this area. Also, any decrease in the blood pump speed will decrease the negativity here, because the blood pump speed or the blood pump is responsible for creation of negative pressure in this area. So we're decreasing the blood pump speed, the negative pressure behind the blood pump will decrease. So the pre-pump arterial blood pressure monitor will read less negative pressure. In the opposite side, what may cause more negative pre-pump arterial pressure? First point, if there is any difficulty in delivering the blood to the blood pump from the vascular access due to any problem in the vascular access. So there is a difficulty to deliver the blood, which will lead to creation of more negative pressure by the blood pump trying to suck the blood from the vascular access. So if there is a kink, clamp, or occlusion of the arterial blood line, may cause more negative pressure in this monitor. If the arterial fistula needle has poor positioning or clotting or infiltration, which will cause difficulty in delivering the blood from the vascular access. Any stenosis of the arterial anastomosis or clotting of the arterial limb of the vascular access of the patient, or if the patient is using venous catheter, it may has improper positioning or clotting. So any difficulty to suck the blood from the vascular access, whatever it is, a fistula or a catheter, will cause more negative pressure in this area. Another cause that may lead to more negative pre-pump arterial blood pressure, if we are using a small gauge needle in the vascular access with a high blood flow rate. In the coming lectures, we will talk later on about the vascular access, and we will talk about different sizes of the needles used and the accepted blood flow rate with each size. But if you are using a small needle size with a high blood flow rate, this will make a difficulty in delivering the blood from the vascular access, which will lead to a more negative pressure in this monitor. Also, if the blood pump speed is higher than the arterial blood coming out from the vascular access, if the patient has a vascular access problem. So the vascular access supplying the blood in a very poor manner, but the blood pump is very high. The idea here is likely the same as having a high blood flow rate from a small needle. And finally, if the patient is hypotensive or has a poor cardiac status, this also will lead to difficulty in delivering the blood from the vascular access, causing a more negative pressure in the pre-pump arterial pressure monitor. And finally, increased blood viscosity, whatever due to high hematocrit or increased blood viscosity because of the ultrafiltration of the dialysis itself, will increase the pressure, will make the pressure, more negative in this area because the blood will be heavy. The viscosity is high. So we will need more negative pressure to suck the blood from this area. Regarding the second pressure monitor, which is the post-arterial pressure monitor, what are the causes of changes in pressure in this area? First of all, causes of less positive pressure. The pressure here is less positive. I mean, the pressure becomes lower. First, if there is difficulty to deliver blood to this monitor, the blood cannot come from the behind to this monitor, as if there is any kink, clamp, or occlusion in the arterial line before the pressure monitor, or if there is air leak after the arterial pressure monitor. Any air leak here, for example, if there is separation of the arterial line from the dialyzer, this will cause decreased pressure in the post-pump arterial pressure monitor. What may cause more positive pressure here? More positive pressure here may be due to increased resistance in any part of the blood tubing set or dialyzer till the patient. For example, if there is here in this part of the arterial line between the pressure monitor to the dialyzer, if there is a kink or clamp or occlusion in this area, or clotting in this area also, will cause high pressure in post-pump arterial pressure monitor due to increased resistance. Or maybe there is an occlusion of the dialyzer because of clotting, also this will increase the pressure in this monitor. Or if there is a problem in the vascular access, in the venous part, that will prevent the blood to reach the patient easily and increase the resistance in the blood flow. For example, if there is venous catheter improper positioning or clotting, or infiltration or poor positioning of the fistula needle, or if there is all of these are problems in the venous access itself. Again, sorry for disruption at this point. Any problem in the vascular access will cause increased resistance to the blood return to the patient, increasing the pressure in the post-pump arterial pressure monitor. For example, the venous access has improper positioning or clotting, poor positioning or infiltration of the fistula needle, or spasm or vasoconstriction in the vascular access itself. Or the second point that may cause resistance to the blood to return to the patient and causing a high pressure in the post-arterial pressure monitor, if again we are using a high blood flow through a small needle. So a small needle gauge will resist the high blood flow that is coming back to the patient, causing high pressure in the post-pump arterial pressure monitor. Finally, if there is increased blood viscosity, this will cause increased resistance and increased post-pump arterial pressure monitor. The last pressure monitor is the venous pressure monitor, which has always a positive pressure. What may cause this pressure to be less positive? To be less positive, if we cannot return the blood back to this monitor, before this monitor, in this area. For example, kinking, clamping, or occlusion of this part, or clotting of the dialyzer. So if you have clotting of the dialyzer, you will find a high post-pump arterial pressure monitor and low venous pressure monitor. Also, any air leak after this pressure monitor will cause the pressure to be lower in this monitor. As for example, separation in the venous line between the line itself and the patient. Finally, what may cause also less positive pressure in this area if the blood pump is slow. If the blood pump is slow, so the blood delivered to this area will be low, causing a lower pressure. The second point, what are the causes of more positive pressure in this area? First of all, again, difficulty to return the blood to the patient. The causes of increased venous pressure monitor pressure, most of them or some of them are the same as post-arterial blood pressure monitor. I mean the factors that are related to the vascular access, any poor positioning in the vascular access, any kinking in the vascular access or the blood line here after the pressure monitor, any poor positioning, any spasm or vasoconstriction in the vascular access. All of these will lead to resistance to the blood returning to the patient, causing a high pressure in the venous pressure monitor and also a high pressure in the post-pump arterial pressure monitor. Also, using a high blood flow through small needle or increased pump speed will cause increased pressure in the venous pressure monitor. Because if we are using a high pump speed, this will cause a high flow of blood through this area, causing high pressure. And if we are using a high blood flow rate through a small needle, this will cause a resistance for the blood flow into the patient vascular access, causing a high pressure in the venous pressure monitor. And finally, also increased blood viscosity, the same, will cause high pressure in the venous pressure monitor and high pressure in the post-pump arterial pressure monitor. The second blood circuit related alarm is the air detector. As we mentioned in the first slide, that the venous drip chamber has an air detector and blood level detector. So the venous drip chamber has a blood level and air detector. If the blood level in this chamber falls below the detector of the blood level due to the presence of excessive air in this chamber, this will be sensed by a form of ultrasound behind this chamber that will trigger an alarm because of the air accumulation in this area and that the blood level becomes lower. And this will stimulate this air detector clamp to act and close this line to prevent the air to enter into the patients, and the blood pump will stop and the machine will give an alarm and the dialysis will be stopped. So if the blood level here falls because of air here, this will stimulate the air detector clamp to act and prevent the air from entering to the patient, and an alarm will act and the blood pump will automatically stop. Finally, we finished this lecture and see you in the coming lecture about the dialysis water unit.